Welcome to Brain Vision.
In the first part of this problem, we have first to calculate the maximum possible amount of shear stress. So let's define the shear stress. Maximum amount of this shear stress is written as a force per unit area. In this case, this force is equals to mu s, which is the coefficient of static friction, multiplied by mg, which is the weight of the object. So from here we can write this shear stress as a maximum shear stress. So this is equals to mu s mg divided by a. By inserting values into this equation we can write here. So this left side will be equals to 0.91 into m, which is equals to 7.2 multiplied by 10 raised to power minus 2 kg into the gravitational acceleration, which is equals to 9.80 meter per second square, divided by the contact area, which is equals to 3.0 multiplied by 10 raised to power minus 2 meter whole square. So this is the length of one side of that square. So from here we can write the maximum shear stress as maximum shear stress is equals to 710 Newton per meter square. So this is the answer to the first part of this problem. Let's move to the second part of this problem. In part B of this problem, we are going to calculate the maximum possible amount of shear strength. So let's write the equation for the maximum possible amount of this shear strength. Maximum possible amount of shear strength. So this is equals to delta x divided by L naught. So from here we can write this equation as maximum possible shear stress divided by S. Here this S is the shear modulus. So this equation can be written as maximum possible shear strength. This shear strength, this is equals to 710 Newton per meter square divided by 2.0 multiplied by 10 raised to power 10 Newton per meter square. So from here we can write the maximum shear strength as maximum shear strength is equals to 3.6 multiplied by 10 raised to power minus 8. So this will be the answer to the part B of this problem. In part C of this problem, we have to calculate the maximum possible shear deformation. That is written as delta x. So we can write the equation for the delta x from the above equation as this delta x, which is the possible shear deformation. This should be equals to maximum possible shear strength multiplied by L naught, which is the length of the material, length of the object. So by inserting values into this equation, we can write here this delta x is equals to 3.6 multiplied by 10 raised to power minus 8 into L naught, which is equals to 1.0 multiplied by 10 raised to power minus 2 meter. So from here we can write this deformation as delta x is equals to 3.6 multiplied by 10 raised to power minus 10 meter. So this is the answer to the part C of this problem. End of the question. Thank you.